Hello, welcome back to Engineering 201 Electrical Fundamentals. We're continuing working on mesh or loop analysis, and maybe even we'll work in a little review on node analysis that we talked about previously. We introduced this subject in the last lecture, so if you're struggling with that, you may want to go back and watch the last lecture. Also, working more problems. I took some of these problems out of the textbook that you're using. Going and finding problems that the answers are available, whether it's in the reading or in the back of the book, is a useful way of testing your knowledge. It's a good way to test your knowledge. So let's try this problem. We'll work this several different ways. This is going to have a few tricky spots that will help us to develop our skills. So I've got this circuit, and we'd like to find this voltage out here, V0. We'd like to try and figure out what that is. Let me get maybe a little better pen here. So what I'm going to do is I'm going to say that I have I1, and I'm going to say that I have around here I2. And actually I2 is going to be equal to IX. But I'm going to put these mesh currents in. So we'll say that this is mesh. Okay? And if I do Kirchhoff's law around here, I notice first if I try and start here and go around this, I'm going to have a problem, because as I move around this, as I get to this point and try and go across there, I don't know the voltage across there. I don't know, I know this is a current source, but I don't know the voltage across it. So what I'm going to have to do is, instead, I'm going to have to pick a path and go around here like that. So let's see what that looks like. I'm going to say that I have 1K times I1 plus then, so that's gone there. I've started right here, gone through there, 2K times I2. Then this is a gain of 6. So these are drops. So I'll say that's minus 6. So I'm taking a drop as positive. Okay, taking drops as positive. So I've got 1K times I1 plus 2K times I2 minus 6. And then I'm going to have plus 1K times I2 gets me back to this bottom. This point is, of course, the same as that one and that one. So I can say then by Kirchhoff's law that that is equal to 0. Well, we could tidy this up a little bit. How many I1s do I have? I have 1K I1, and then plus 3K I2 is equal to 6, and that's a nice equation. The only problem is that there's two unknowns, I1 and I2. So I need a second equation. I'm going to have to come over here and note that if I look at I2 would be going this way, I1 would be going that way, so I2 minus I1 is equal to this current source, is equal to 2 IX. Okay, and this, if this happened to be a little more simple example where this was maybe just 4 amps or something, we'd say this was 4 amps. But in this case, it's a little trickier. It's related to some current somewhere else. Well, IX happens to be equal to I2, doesn't it? So I could say then that I2 minus, keep that a minus, I2 minus I1 is equal to 2 I2, or that minus I1 is equal to I2, or maybe I'll say finally that I1 is equal to minus I2. I'm going to substitute that in then over here, and when I do that, I'm going to come up with what? Minus 1K I2. Because if I1 is equal to minus I2, I can do that, get the negative sign there, plus 3K I2 is equal to 6. So I'm left with what? 2K I2 is equal to 6, or I2 is equal to 6 divided by 2k, which gives me what, 3 milli? Or I could say that I2 is equal to 3 milliamps. Now that I have I2, I could get I1 be minus 3 milliamps, but what I really want is I can then say that V0 is equal to I2, that's going through there, so it's going to be I2 times 1K. So I have 3 milliamps times 1K, these are K ohms, we just said K for shorthand, so that gives me 3 volts. So our answer there is 3 volts. Now, a lot of times students in the past, they've talked about this as a super mesh or a super loop. I don't know that that notation is particularly used, but it does look a little bit like where we had to have that super node when we were doing node analysis. There was a source that was going to cause us problems, a voltage source in that case. So we essentially went around it and we had to write another equation. Here we went around the source and we had to come over and write another equation. Now, I'm going to do this problem again. In fact, I'm going to do it a couple more times. But the second time, I'm going to do it with what we would call loop equations. So I'm going to leave this I1 here and then superimpose on top of it maybe a IB that goes around like that. So let me try that. So like I said, I'm going to leave this I1 here. And then I'm going to say that there's another current that goes around like this. I'm going to call that maybe, so I know this is a little different, maybe I will call this IB. So we've got I1, the current just in this little mesh, and then we've got IB that's going through here. And technically, this would be loop analysis. Now again, nothing has changed. I still cannot go through this source. I'm going to have to take my path around the perimeter of this thing, like this. So that has not changed at all between these two. Well, let me do that then. So I could say if I start at this point, again, I'm going to take, what did I take in the last time? Drop as positive. So again, taking drops as positive, now I will have 1K. What's the current through this 1K? Well, it's I1 and IB, isn't it? So I'll have I1 plus IB. And then I'm going to add to that 2K times what's the current through that? Well, it's just IB because I1's only hanging around here. So I've got 2K times IB. And then I have a gain of 6, so it'll be minus 6. And then plus, again, the current in there is IB, so I'll have 1K times IB. That gets us back to our base point down here, our starting point. We can say then that that's equal to 0. So when I tidy this up, I have 1K times I1 plus, 1 and 2. So we've got 3 and 4. 4K IB is equal to 6. So again, that's a nice equation, but two unknowns, I1 and IB. So I'm going to have to go over, and very much like I did in the last one, I'm going to have to note what? I'm going to have to note that, let's see, what's the current going through here? Well, IB goes around this, so the only current through here is this I1 that's going the opposite way, so I can note that I1 is equal to minus 2 IX. Okay, that this current here, I1, is the same as this, except it's in the opposite direction. So I can say I1 is equal to minus 2IX. Well, IX, and again, if this was a 4 amp source or a 10 amp source or something, it'd be fairly easy. I1 would be equal to 10 or 4, whatever the case would be. This is a little more confusing because it's a dependent current source where we take 2 and multiply it by IX. So I need to know what IX is. Well, IX happens to be IB. So we could say that this is IB. So I could say then that I1 is equal to minus 2 IB. And I can then substitute that into here. So when I substitute that into here, I'm going to get something like this. I'll have, what, 1k times I1, so 1k, and then instead of writing I1, I'm going to have a minus 2 times IB plus 4k times IB is equal to 6. So what do I have? I've got minus 2k IB and 4k IB, so I have then 2k IB is equal to 6, and IB turns out to be equal to 6 divided by 2k, which is equal to 3 milli, or I could say 3 milliamps, because this is really k ohms. So I'd have 3 milliamps. Now again, IB is the current over here, so I can note then that V naught is really just equal to IB times 1 k ohm. So I have 3 milliamps times 1 k ohm is equal to 3 volts. 3 volts. Okay. Probably, I tend to do more problems with technically the mesh analysis. If you want, I brought this out so you could see the difference between the mesh and the loop. Both very standard methods. People tend to use those terms interchangeably, but they both work on this problem. In fact, I'm going to switch gears rather substantially here and try the same problem, but this time with node analysis. Keep practicing that node analysis. So let's do that. So we're going to do node analysis here. And maybe I'll change my currents up a little bit. I got 2Ix there, I got Ix there. So let me just say I'm going to assume that this is Iy. So I've got an essential node there, an essential node there. I'm going to take that as the reference. I'm going to call this then the voltage V. And I can say then that with Kirchhoff's law that Iy plus Ix, that's leaving, has to equal what's going in. That's 2Ix, isn't it? So Iy is leaving, Ix is leaving. They're on one side. The 2Ix going in is on the other side. So let's see. I subtract Ix from each side. I get Iy is equal to Ix, isn't it? And what is Iy? That's this current here. So if I take that voltage there, which happens to be V, and divide by 1K, that's Iy, because the voltage across there is the same as the voltage across there, which we've defined as V. And then I need to talk about Ix. What's Ix? Ix is a little tougher, isn't it? We could introduce this term V naught in here. I think I'll avoid introducing another variable, and if I were to look at the right-hand side of this circuit, could I replace this circuit with something that looked like this? This would be 6 volts, and this would be this 1K and that 2K, so this would be 3K. Could I do that? The question is, would this current Ix here really be the same as this current Ix over here? Now you note this V naught. This is just a notation here. There's no current through here. The current in here is equal to 0. This is like you putting the probes from the voltmeter in laboratory, a probe right there and a probe right there. So there's no change there. All I've done is taken this resistor and moved it up and combined it with that one. So of course Ix would be the same. Now this one is then a little bit easier to envision, because I need to then find this voltage across here, which is going to be 6 plus V divided by 3K, right? The voltage here is the voltage at this point, that's V. And the voltage here, because we're referencing to this bottom part, is from here to here, that's 6. and from there to there is V, isn't it? So I go 6 plus V, that's this voltage, divided by 3K. So a little tricky. Like I said, a lot of students are a little more comfortable with node or mesh analysis, but it's good to be able to get through these problems. I think what I'll do is I'll multiply by 3K, so I have 3V is equal to 6 plus V. Is that right? 3K, yeah, 6 plus V. So now I have, subtract a V from both sides. 2V is equal to 6. V is equal to 3 volts, right? V is equal to 3 volts. Now that's the voltage here. Right there is 3 volts. So what's the voltage out here going to be? Well, we could say then that V naught would be equal to what? IX times 1K, right? What's IX equal to? Well, let's see. Do we have a value for IX? Yeah, it's right there. So it's 6 plus V divided by 3K, which is going to be 6 plus, we got this V of 3 volts, divided by 3K, which is 9 over 3K, so this is 3 milliamps, right? So I take this 3 milliamps and I put it up into here, and we note then that V naught is equal to 3 milliamps times 1K, which is equal to 3 volts. Okay, 3 volts. I think that's what we got before on that, so I think we are in a good shape there. Let me double check the work here. 3 milliamps, yep, 3 volts. So when you do a problem like that, you learn a lot doing it different ways. You also build confidence in the answer. We got the answer essentially 3 different ways. I think we can be confident with this. Unfortunately, there's lots of wrong ways to do the problems. That's why we encourage you to do your homework, do the sample test, and really practice this a great deal. Well, let's move on. I've got a couple more problems that I want to practice with today. Let me number these pages. I think we did that was first, second. This is third. So we're going to try this problem. So this is a completely different problem. We've worn that one out. That last problem we did 3 different ways, so we're tired of it. So we're going on to this problem here. And I'd like to find I naught. And I think I'm going to do this with node analysis. You could do it with mesh analysis. It'd be kind of interesting with mesh analysis, because if you came along here and put a current in here, probably would be 4 amps, and you'd have to use our technique that we had on that last problem where we had that so-called super mesh or super node. That's kind of probably not a very common way to describe that, but we'd have to do that with this one here and then move around this entire thing. But I think this will lend itself nicely to node analysis, so let's try it with node analysis. So we're going to take this as V1. I could take this as a V2. I could say that this is I1. That's I naught. We've got this current here. Why don't we say then this is I2? And of course we're looking for I naught, aren't we? So if I talk about Kirchhoff's current law at node number 1, we're going to come up with the equation what? 4 is going in, and I1 and I naught are leaving. So we've got 4 is equal to I1 plus I naught. I1 leaving, I naught leaving, 4 is going in. And if we do a similar thing, Kirchhoff's current law at 2, what are we going to get? Well, we've got I naught going in, we've got 6 leaving, and 2 leaving. So we could say that I naught is equal to 6 plus I2. That's going in, that's leaving, and that's leaving. And incidentally, I just arbitrarily put in I1 and I2. We may get a negative sign on those. So let's see. We could, if we wanted to, just substitute that back into there. Wouldn't that work? Well, let's see. We'll work through these problems. So I've got 4 is equal to, what's I1 going to be? That's going to be V1 divided by 1. And then I0, that's a little tougher. You got to find that voltage there. So we're going to have what? Minus V2 plus V1 divided by minus V2 plus V1 divided by 1. So I could say that this is 4 is equal to, I'm going to have a V1 plus a V1, so I have 2 V1 minus V2. Then over here I've got I0, which is again be the V1 minus V2 divided by 1 is equal to 6 plus I2. That is going to be V2 divided by that 2, because in that voltage that's V2, so V2 divided by 2. Got to multiply everything by 2 there, so 2V1 minus 2V2 is equal to 12 plus V2. And I get then, let's see, subtracting a V2 from each side, we get 2V1 minus 3V2 is equal to 12. Well, to get this current I0, I've got to solve for both V1 and V2, so there's not necessarily a shortcut there. See, what would have happened if I would have plugged that equation in there? I1, we would have had a V1, and then this, we'd have had 6 and V2. Yeah, that might have been a bit of a problem because I would have lost some of those. Well, I can experiment with that later. But let's see if we can solve these equations for V1 and V2. So I'll write this as 2V1 minus V2 is equal to 4. And then I'm going to write this one as 2V1 minus 3V2 is equal to 12. And I will multiply this by a minus 1. So when I add them together, I get 0V1 and minus 2V2 is equal to 8. So we've got then V2 is minus 4 volts. Minus 4 volts. Well, let's see, if V2 is equal to minus 4 volts, you could plug that into here. So substituting that in, we would say that we could substitute it into this equation or this equation. I'll just do this one because it's handy. So I have 2V1 minus 3 times a minus 4 is equal to 12. So that comes up as a positive 12. So 2V1 plus 12 is equal to 12. I subtract 12 from both sides. 2V1 is equal to 0. So V1 is equal to 0 volts. So kind of an odd result, but that worked there. And that's why we probably would have had a little bit, it would have been a little bit tricky if I were to have substituted that into there. Maybe we could play with that. What would we get? We'd get 4 is equal to I1 plus I0, which is 6 plus I2. So I'd have minus 2, taking the 6 over there, is equal to I1 plus I2. So minus 2 is equal to, what do we have for I1? That's V1 divided by 1 plus I2, which is V2 divided by 2. Multiply everything by 2. Minus 4 is equal to, what was I doing? Multiplying by 2, right? So minus 4 is equal to 2V1 plus V2. We would have had a bit of a problem there, wouldn't we? We'd got one equation, two unknowns. So I think that would have been presented a difficulty. We would have ended up coming back to these equations. But let's see if our answer, what if we recognize if V1 is equal to 0? If we substitute that in there, what do you come up with for V2? Minus 4. So it does work. We would have had to have found one more equation to either find V1 or V2. So sometimes you have to be a little bit careful with your solution technique, and this was exacerbated because that answer is equal to 0. The last way, like I mentioned, if you would have put currents in here, that current is really easy. That's just 4 amps, right? But when you put a current in there and a current in there, then that becomes a little more difficult to write a mesh or a loop equation around there. So while no, it had some pitfalls, it is probably the easier method on this problem. Yeah, good problem to practice. Did I answer it? Oh yeah, I got to be careful of this. I didn't answer it yet, did I? I found V1 and V2 and was so happy about that I got sidetracked. What I'm looking for is I naught. So, what's I naught? Well, I naught is equal to V1 minus V2 divided by 1. So I can say V1, that's 0, minus V2, which is a minus 4, divided by 1, which gives me 4 amps. So I naught is 4 amps. That's another good lesson. I'm not going to say that I did that on purpose, but that's another good lesson that you really need to make sure that you check and make sure that you've answered what you were supposed to. So a good problem, good solid problem, has a few little tricky spots you have to be careful of. So the last problem for our lecture, and really the last problem is formal problem. As we do node or mesh, we'll be doing those techniques a lot in the future, but it'll be for some other purpose rather than simply to practice node or mesh. We'll go on with some circuit simplification techniques, superposition and source transformation and things like that, Thevenin's theorem. But let's try this problem. What I would like to do with this one is I would like to try it with a mesh. Now you might say, well, if I put a mesh in here and there and there and there and there, I've got, what, 1, 2, 3, 4, 5 equations. I don't think I want to work that hard. So I think what I'm going to do is I'm going to go ahead and simplify this a little bit. If all I'm looking for is V naught here, I think what I'll do is I'll recognize that these two resistors, they're in parallel, right? So if I have 1 in parallel with 2, that gives me what? Product over sum is going to give me 2/3, isn't it? Yeah. And then I recognize that these two are in series. So I have 1 plus 1 gives me 2 ohms, and that's in parallel with that. And 2 in parallel with 2 gives me 1 ohm. So I can simplify this circuit rather dramatically and say that I have 6 amps here. I've got then this resistance, the combination of those, which is 2/3 of an ohm. I've got this 1 ohm that's going to remain there. And I've got this combination, which is 1 ohm. And then I don't want to forget this 2 amp source. So I'm going to submit that as the similar circuit. You might say, well, you lost this. When you combine these two, you lost V naught. Indeed, that's true. But I think if I figure out maybe the current that's going through this thing, I can then use some current division and I think get V naught, because that current would just then divide between here and there, and I should be able to work that out. So you could charge through this and not simplify it, but I think simplifying is going to make it a lot easier. And I wanted to show this, that the information that we studied before, we're not leaving that behind, but you could and can combine that with node and mesh analysis to hopefully make things easier. Well, let me put a mesh in here. I'm going to say that this is I1. I'm going to say that this one in here is I2. And I'm going to say that this one in here is I3. And we can note right off that I1 is equal to what? Well, I1 has to be this 6. In fact, if I were to try and do Kirchhoff's law around here, I couldn't, because I don't know the voltage across there. So luckily, I recognize that as 6 amps. And likewise, I could say that I2, that's the current up here. I'll be real clear on that. That's I2. That is opposing 2 amps, so it's going to be what? Minus 2 amps, isn't it? Well, this is getting even easier. We're going to have to work on this one. I'm going to have to go around this perimeter here like this. So let me go ahead and write that. I could say Kirchhoff's voltage law about I3, essentially, about the loop for I3. So if I start right here, I'm going to have what? 2/3 of an ohm times what's the current, net current going up like that? That's going to be I3 minus I1, isn't it? And then when I get up to here, I'm going to have 1 ohm times what's the net current going to the right? That would be I3 minus this current here, because that's opposing it, I2. And then finally, the current going like that is simply I3, so I will have plus, because I'm taking drops as positive, so I've got plus 1 ohm, that 1 ohm there, times I3. That gets me back down to here, which is the same point as there. My starting position, Kirchhoff says that's equal to 0. So I could tidy this up a bit. How many I1s do I have? I've got minus 2/3 I1. And this is actually a voltage. Well, let me write this out and we'll talk about that. So I've got that many I1s. How about I2s? Minus 1 I2. And then how many I3s? Plus, I got 1 I3, 2 I3s, and 2/3. Yeah, 2 and 2/3. I3 is equal to 0. These are actually voltage terms, because this is, remember Ohm's law, V is equal to IR. This is a resistance, 2/3 of an ohm, 1 ohm, 2 and 2/3 of an ohm, times a current, I1 or I2 or I3. So these are voltage terms. Has to be, because it's Kirchhoff's voltage law, right? Well, let's see. We can make our substitution. I know that this is minus 2/3 times 6 minus 1 times what? A minus 2 plus 2 and 2/3 times I3 is equal to 0. So what do we have here? We have 2 and 2/3 I3 is equal to, let's see, this is going to be what? A negative, and a negative becomes a positive. So when this positive goes to the other side, it becomes negative. So I have a minus 2 here. And then I have a positive and a negative, so that's going to be a negative. It goes to the other side as a positive. What do I have? 3 goes into 6 twice, and I will have 4. So I could say I3 is equal to 2 divided by 2 and 2/3. Let me get a number for that. Yeah, I think that's right. 0.75. We could say 3/4, but I used the calculator. I broke down. I'll put it in decimal form. So 0.75 amps. Okay, so that's I3. Well, I'm not interested in I3. I'm interested in V0. So let's see if we can get that. So page 5. Check with one more here. So I've got that I3 is 3/4 of an amp. So from this picture here, what's this voltage here? I could say that that voltage there, that V is equal to, that's going to be equal to I3 times 1 ohm, which is 0.75 amps, times 1 ohm, which is 0.75 volts. Is that right? I think so. So what I'm getting there is, by finding this voltage here, I now have found that voltage there, haven't I? Which I could split between those. It's actually going to be an even split because those are the same. I could say, but so by voltage division, V0 is equal to this voltage V, which is 0.75 volts times 1 ohm divided by 1 ohm plus 1 ohm, which is half of 3/4, which should be 3/8. Okay. Now, you might say, well, I thought you were saying when you combine these resistors, you were going to maybe use current division to work it back out. Well, let's try that. So we said that this I3, this current here, was what? 3/4 of an amp. So if I use current division, I'm going to divide it between this and that, right? So maybe I'll say that this is I don't think we've used I0. Let me talk about I0. So by current division, I0 is going to be equal to this total current, which would be 3/4, because I mean this 3/4 would have to split between there and there. So 3/4 times not this resistance but this resistance. So I'll have 2 ohms divided by, we have to look at the sum of these, which is 2, and that's 2, so you're going to have 4 ohms there. So this turns out to be 3/8 of an amp. So if this current here is 3/8 of an amp, that current there is 3/8 of an amp. What is 3/8 of an amp times 1 ohm? Well, that of course gets you 3/8 of a volt. So we've seen that before. So that's a good problem to illustrate a couple things as we finish up on this section. A lot of times you may want to think about trying to simplify a circuit. There's really no reason. I mean, you could argue, well, we had to mess around with current or voltage division here, but there's really no reason at all for not combining those. That made our life a lot easier. If we would have had, if we would have left those, we would have had a lot more mesh equations that we would have had to have hassled with. So I think that's a good example, a good way to wrap up our work in mesh analysis and loop analysis, and also reviewing the previous work that we did with node analysis. So I'll encourage you again to keep working on your homework, keep practicing on these problems. Take one of these problems and cover up my solutions and see if you can do it on your own. So thank you for watching, and take care till next time.